Hi everyone. So let me introduce you to another thing that synchronized blocks safeguard us. Let's look at this main function. It has some piece of code. So if you want, you can just pause the video and read this code for a while. Let's do that. Okay, if you have read this code, I also need to show you the worker class. So this is a worker class which takes in an instance of number store and simply calls number store dot increment. Now for that, we need to also look at number store. Number store has 4 numbers x, y, z, w. Each of them are initialized to 0. Okay. Now there is an increment method which simply adds 1 to all of them. Okay. So you can see one thing, that initially everything is 0, and whenever increment will be called, they will be incremented by 1 unit. So from 0, 0, 0, 0, they will all become 1, 1, 1, 1. And then if increment is called again, they will all become 2, 2, 2, 2. So basically after every invocation of increment, I would expect x, y, z and w to be exactly equal to same. Okay. Now there is a get x, get y, get z and get w. Okay. So these are simple getters. Okay. Let's head back to our main function. So here we created an instance of number store, and now we are running an iteration for 10 power 5 times. In each iteration, we are instantiating a new thread with a worker. We know what this worker does. This worker doesn't do anything special. It simply calls the increment method on that number store. Okay. So yeah, we pass in this number store inside that worker so that it can call. And then the first thing that we do is we figure out the current value of w from the number store. Okay, so when the first iteration runs, the current value will be 0. After figuring out the current value, we launch the thread. And after launching the thread, there is a while loop. Now this while loop will keep on running as long as the value of w read by us hasn't changed. See, whenever you launch the thread, what this thread will do? This thread will ensure that your run method inside the worker runs, and that run method will make an attempt to increment the value of x, y, z as well as w, isn't it? So if you remember, this increment method will increase all of them in this manner. And when I look at this piece of code, it gives me a very clear idea that first x will be incremented, then y will be incremented, then z, and finally w will be incremented. Okay, so by this conviction, if I look at this particular while loop, it will only break when the value of w has been incremented. Okay, now when the value of w has been incremented, it is sure that the value of z, y and x also would have been incremented, isn't it? Okay, now when I come back to this method, there is an if condition. If you haven't read this if condition, you should pause the video and read it once again. Let's do that. So all that this condition is saying, that if x, y, z and w are not equal to one another, then let's print their values. This is all that it says for now. But guys, should it ever happen? Just pause and think for it as well. The answer is ideally no. Why? Because we all know that initial value of x, y, z, w was same, and every time they are incrementing by the same magnitude. Okay? And moreover, if w has incremented, then z, y, x would also have incremented by the same unit. See, if you look at one important thing over here, my while loop had a condition for w. It did not have a condition for x. It did not have a condition for y or z. Let's say if it had a condition for z, then it might have been possible that the value of x, y, z have been incremented, but w hasn't been still incremented. A context switch probably happened. But because of this condition, even if a context switch happens after incrementation of w, then it is guaranteed that increment of x, y, z also would have definitely have happened, right? So ideally this if condition should never ever evaluate to true. That is what our expectation is. But if I run this particular code, Let's just see whether some lines actually get printed or not. So to our surprise, we can see there are a lot of lines that are actually getting printed. You can just read through few of the lines. So see, the first line got printed after almost 5,000 iterations. So till 5,000 iteration, X, Y, Z and W, all of them were in super sync. But now we can see that the value of X is 5401. And the value of the last thing, which is W, is also 5401, but the value of middle things is 5400 only. So by look and feel of it, we can sense that the X and W have been incremented, but Y and Z have been left over. Why so? Is it even possible? It doesn't look good, right? So can you possibly reason this thing? Can you think why it could possibly have happened? Just pause and think about it. So if I take you back to this main function, first of all, ask yourself one question. Do you see any possibility for race condition over here? Just pause and think. The answer is no. No race conditions at all. Why? Because we always wait for the current thread to terminate. Only when the current thread has terminated, we go on to the next iteration where we launch another thread. It means that it will never ever happen that two or more threads are mutating the value of any variable, whether it be X or Y or Z or W. It's never ever possible. So the first thing is there are no race conditions at all. Nothing to worry about that. Okay, second thing that a lot of you might have guessed, and if you have guessed, you are right, that might be memory visibility issue. So you might be thinking that, hey, here there are two threads in picture for each iteration. The first thread is your thread T, which is your writer thread, and the second thread is your main thread, which is the reader thread. And it may be possible that the change to the variables made by thread T is still not visible to your main thread. So yeah, this is one reason for sure. And you saw that happening right now. Okay. In certain iterations, the changes were all visible, but in many iterations, they were not visible also. So memory visibility is really a big issue, right? Okay. Apart from that, there is one more issue that I wanted to bring your attention to. So guys, for that, you need to understand how our JVM, which is Java Virtual Machine, or our instruction optimizers, how they internally work. So, at times what they do is when they see that there are certain lines of code, and if it is possible to reorder those lines of code in order to achieve some performance benefit without changing the semantics of your program, then it is made possible. So in that case, what really happens is that the lines of code that you write, they undergo rearrangement. They are basically permuted. They are reordered. Now, that reordering is done to achieve some kind of performance benefit, and that too without changing the functionality of the program. See, here, even if these lines of code are permuted, then the semantics of program is not going to much change. Yeah, you can also argue that there doesn't seem to be any performance benefit by looking at this particular scenario. But yeah, still these rearrangements can at times happen. Yeah, so it means that if there is a thread, and if that thread has an expectation from the other thread that if it has completed the last line, then all the previous line would also have got completed, then it is not right. Why it is not right? Because the instructions might have got reordered, might have got jumbled up. Now, when I tell you this thing, then I also need to tell you the solution for this. The standard solution for this thing is that whenever you want these kind of instructions to not be basically jumbled up at all, then in that case, you can just put a synchronized block over here. So we know that all the threads have the same instance of number store. So we are synchronizing on the same instance of this number store. So when I put this thing up over here, then one thing that is guaranteed is that these instructions are not going to be jumbled up. And going by that idea, what I would expect is that if my W has changed, then X, Y, and Z also would have changed for sure. Okay, but only this is not enough, because if I run this program now, you still should be able to reason it that memory visibility issue still can be there, right? Because the reader thread should actually be reading the value of X, Y, Z, and W after synchronizing on the same lock. Okay, so for that, I would want to put a synchronized keyword over here. Now, if I put up this synchronized keyword in all the getters also, then it will be guaranteed that there won't be any memory visibility issue, and the rearrangement issue, we had already taken care of that. So now if I run this program, you can see that the program has finished without printing any line. So it means that there was no such issue at all. So you can rerun it again and again, and you can see that these problems won't happen. So guys, we have seen that how many different problems could otherwise have been there if we would not be guarding our critical section, if we would not be using synchronization techniques. So we have seen things like race condition, we have seen things like memory visibility, we have seen things like instructions rearrangement, and let me tell you, there are more to come, but you should first try to get a very, very clear understanding of all these things. You should also feel inspired to experiment few things on your own. Just write some program and just see for these things like race conditions, memory visibility issues. Just play around with threads.